Alright, welcome back. Today we're taking a look at the Kodachromium Lab, Part 1. So doing the calculations to figure out what amount of energy is released from these different energy levels. Alright, so we already have one example worked through with us. So we have our atom. It looks like this. And we have an electron falling from the 7th energy level. It's the 7th ring outside the nucleus. Here's the nucleus. 1, 2, 3, 4, 5, 6, 7. Falling from the 7th down to the 1st. So that's n equals 7 to n equals 1. And we've already got that calculation right here. So energy from the 1st, energy to 7th. Find the energy. Once we're able to find the energy, we're able to find the frequency. And with the frequency then, we're able to find the wavelength. Big thing about the wavelength is that we needed it to be in nanometers when we finished so that we were able to assign it a color. So these are all in nanometers. So those are the steps we're going to work through here. As an example, from n equals 6 to n equals 1. So this is from the 7th energy level down to the 1st. This one will be from the 6th energy level down to the 1st. So our change in energy, this delta symbol, it's a triangle, represents the change in energy, and that's always going to be your final energy, so F for final, minus your initial energy. So where you ended up, minus where you started. For this particular one, again, we're going n equals 6 to n equals 1, we need the energy of the first energy level. We're starting at 6, and we're falling to 1. So we're ending at 1, that's our final area, and we're subtracting the 6th energy level, which is where we started. Where do we get those values? So we reference the first sheet, and here it tells us at each energy level what the amount of energy is. So we're starting on the 6th energy level here, so that's 1.128 times 10 to the negative 19th joules. And I'm sorry, that was the energy at the 6th level, so we'll use that second. Our first energy level is here, n equals 1, 6.088 times 10 to the negative 19th joules. So I'm going to go ahead and record that. .088 times 10 to the negative 19th joules minus, and now is where we're going to add in, or put in our n equals 6 energy level. We can go ahead and calculate that now and find our change of energy. 6.088, second big E, use that big E button. Negative 19 minus 1.128, second big E, negative 19. And I got a value of 4.96 times 10 to the negative 19th joules. Now here's the problem. I'm going to erase. I need more significant digits. See how these are all times 10 to the negative 19th? That means they all have the same last placeholder. This one goes 3 past the decimal. This one goes 3 past the decimal. So my final answer should also go 3 past the decimal. I know my calculator only reported 4.96, but sometimes we got to be a little bit smarter and know that if there's not another number, it's a 0. So there we go. Now we have appropriate significant digits. Okay, so now that we have our energy, what are we going to do with that? Well, now that we have an energy, now we can solve for frequency. In order to solve for frequency, that's this, looks like a V, it's really the Greek letter nu. In order to solve for it, we need to get it on a side by itself. So we'll divide both sides by h. Now we can plug in our variables. 4.960 times 10 to the negative 19th joules is our energy. H is Planck's constant, 6.626 times 10 to the negative 34th joule seconds. And that will solve for nu for us, for our frequency. Pull out my calculator. I'm going to use that big E button, 4.960, second big E, negative 19. That's the top number there. Divided by 6.626, second big E, negative 34. Press my enter button, and I get a big long number. Let's check for significant digits. 4.960 has 4 total significant digits. 6.626 has 4 total significant digits. So my number should have 4 significant digits. But this is not my final answer, so I want to carry at least 2 extras so I don't have a round off there. 7.485. There's my 4 significant digits. Now again, I want to carry the next 2, the 6 and the 6. I'm going to underline them to show that they are not significant. And then don't forget about your exponent that says times 10 to the 14th per seconds. The joules divided by joules cancels out. We're left with seconds on the bottom. So there it is, seconds on the bottom per second. Which is good because that is what the unit for frequency is. Alright, fantastic. Next up, we need to take a look at converting this frequency into a wavelength. So the formula for that, speed of light is wavelength times frequency. I'm just going to skip over this part here. You guys were doing all this on a separate sheet of paper, so no need to get worried about that being in our way there. Alright, so I'm looking for wavelength. I have my frequency, and the speed of light is always the same. So to get lambda on a side by itself, I would divide both sides by nu. Now I can plug in my variables. Again, c is the speed of light. It's a constant. It's always going to be 3.00 times 10 to the 8th meters per second. And nu, we solve for up above, 7.48566. I'm going to underline those 2 digits because they are not significant. Times 10 to the 14th per seconds. When I do that calculation, I will get lambda, wavelength. 3.00 second big E, 8, divided by 7.48566 second big E, 14. Press the compute button, and there we go. Lambda 4.00 766,265 times 10 to the negative 7th. I carried a lot of extra digits here. And the important thing is that this is meters. So per second, meter per second, divided by per second. Per seconds cancel out, and we're left with meters. Let's check for significant digits. 3.00, that is a measured amount there. So that's only 3 significant digits. This one has 4 in it, but we're going to be limited to the 3 from up here. So 4.00766, there's my 3 significant digits, the 4.00. The rest of these are all insignificant. So I'm going to underline them. Don't need to get rid of them. I'm not quite done with the problem yet, but I'm going to underline them to remind myself later that they are not significant. So final step here. Alright, final step is that we need nanometers. We have meters. So we need to convert our wavelength in meters to a wavelength in nanometers. This goes back to the factor label that we did at the beginning of the year. How many nanometers are equal to 4.00766.265 times 10 to the negative 7th meters? If you don't remember your conversion from nanometers to meters, hey, well, you can look it up and try to memorize it, or you can just look up above. We did that same calculation up above up here. So 1 meter has a value of 10 to the 9th nanometers. That'll get our meters to cancel out. We're left with nanometers, which is what we were looking for. Wonderful. So now we just have to compute. I should underline all these numbers that were not significant. 4.00766265, second big E, negative 7, times second big E, 9. So the way I can enter a 10 to the 9th is just that 10 is represented by the E, caret 9. So just E big 9 is the same thing. Press my enter button, and voila. Now I am ready to use scientific notation, sure, but significant digits, proper significant digits as well. I only have 3 significant digits. I started the underline at the 7, so the 4, the 0, and the 0, the only significant digits, that's 3. My final answer should only have 3 significant digits. 4.00, there they are. 7 is enough to round up, so 4.01. Don't forget, we've got that times 10 to the second there. So there we go. 4.00 times 10 to the second nanometers. That's 401 nanometers. I look back at my range of colors. 401 nanometers would be right there, just inside of the violet color. So this one would be violet light. And that's what we're doing for part 1 of the Kodachromium activity.